In today's video, we're going to learn how to interpret lab data and how to use a lab data chart to do some calculations. So I thought it would be a good idea to do this lesson because it's a very popular question that comes up on AP free response chemistry exams. So to start off, I wanted to do a summary lesson. So this question is coming from, I believe, the 2014 AP exam. And I actually didn't even include the question. I just want to look at this data and interpret what's going on because it can be a little bit overwhelming when you're given, a data chart and then in this case this diagram, which by the way, the diagram will be very helpful for me in this question or in this kind of scenario. So let's look at this first, and then when we're done, we will solve a couple sample questions from previous exams that have a similar setup. Okay, so in this scenario, it's actually very helpful that they've given me a diagram because the diagram actually relates to this data table. So for example, where it says mass of the empty beaker, I'll number it. That's represented by number 1 on the diagram. And then if we continue in this lab step, as I added M, I'll call this step 2, and I'll label step 2 on my chart. The mass of the beaker with the metal M added, it increases obviously. So I'm actually going to also call this metal. It's a metal M, and what I'm trying to do is just visualize what's going on. And although, again, like I said, there's no question right now, I'm just going to actually take the difference between these two values, because if we do that, that will give me the mass of the metal, or the mass of M. So I'm going to say that the mass of M is 126.549 grams minus the empty beaker, which is 125.457 grams, and that will equal 1.092 grams, okay? Now, in step 3, I've added iodine, okay? And again, it correlates with the data table because it tells me that the mass of the beaker plus metal plus iodine is 127.570 grams, and that's what's shown to me in this picture that I've labeled 3. Okay, so actually knowing that, again, I can derive some information out of this. If I take the difference between this value and this value, so the previous mass value, that will tell me how much iodine I have as well. So let's write that down, that the mass of iodine equals 127.570 grams minus 126.549 grams. And that gives me a mass value of 1.021 grams of iodine. Okay, and as we go on in this experiment, what you can kind of see is I'm creating some sort of ionic compound, which is a combination of a metal and a nonmetal. And I've added in actually this next part where it says added water. It's not really shown to me in the data table per se, but it says here, you add water, you allow the two things to come together and react, and then you get your some sort of aqueous part and then some leftover solid, some leftover M. Actually, and that's kind of important as well, because leftover M indicates that this is actually my excess reactant. And then if we go back up to the iodine would be my limiting reactant. Okay, and again, I'm not sure if I actually need to know this for the question, because again, I took the question out, just trying to illustrate what's going on. And then what's going on here is the solution is collected in a test tube and it gets heated. So we're basically trying to dissolve, or excuse me, not dissolve, we're trying to evaporate all the water. So all the water in this, this Mi2 is aqueous. So if we actually get rid of all the water and evaporate it, the Mi2 compound will come together as a solid and kind of precipitate at the bottom. So this represents step 4, this test tube, where it says the mass of the Mi2 after the first weighting. Okay, usually we do this a couple of times just to make sure all of the water has evaporated off. And then we reheated it again. So I'll call this step 5, and also in my data table, the mass of this ionic compound after the second weighting, and we see that it's actually the same thing, which is good. But you try to evaporate it really well to prevent any sources of error and to really try to purify that compound. Okay, so that is kind of my thought process of how do I interpret a data like this. So let's move on now and try to solve the question together. So this one is, again, from one of the older AP Chem exams, and this one does not actually give me a diagram. So I'm going to try to sketch what's going on just to mimic what we saw up here, okay? And then we'll solve a sample question together. So it says here that a student is trying to figure out how much iodide is in a tablet containing Ki. So as I'm reading on, it says here a tablet is dissolved in 50 milliliters of distilled water. Okay, so let's just try to visualize this. So let's say I've got a beaker, I've got 50 milliliters of water, distilled water, and then I've got a Ki tablet, and this is going to get dissolved in here. Okay, so that's just my visual. And then what I'm going to do is I'm going to put in some excess lead-2 nitrate into the same solution. So now that the Ki is dissolved, we'll just draw like this. We're going to add some PbNO3 Okay, so that will go in there as well. And when you add that in, what happens is you get a precipitate. So let's draw like this. We have a precipitate form. I'll just label it PPT as for precipitate. And then you are going to basically get rid of all the liquids, try to isolate that precipitate, and then you want to do some calculations about that solid that's left over. So what we're going to do here, it talks about here using a filter paper. I can see that in my data table as well. So I'm going to have like an empty filter paper here first, and then I'm going to dump the solution, I guess through a funnel or whatnot, but I'm not going to draw maybe the whole thing. So here's the filter paper again, and let's pretend I was able to get the precipitate on there. And so this is also going to be, drying, and we're going to dry it, 1, 2, or 3 times. We're going to let, again, all that water evaporate off so I can purify that product. Okay, now with that visual being known, let's look at the question here. Again, there's actually multiple parts of the question, but I just took one part of it. Calculate the number of moles of precipitate that is produced in the experiment. So the precipitate, I actually wrote down the chemical equation. And if you guys remember from solubility rules, my products in this reaction will be potassium nitrate. This is aqueous. Now, this actually was not given to me, but I remember from solubility rules that all nitrates are soluble or aqueous. So my precipitate, it must be this PbI2 or this lead-2 iodide that forms. So I've labeled it as a solid. And okay, so now that we know that, this is what I want to try to find, right? How many moles of precipitate did I form? So I can use my lab data to figure out the mass of this precipitate. And what I can see from the data table is after I've dried it the third time, the mass of the precipitate and filter paper is 1.698 grams. So we'll pretend this is after the third drying. So this is 1.698 grams. The empty filter paper is 1.462 grams. So if I take the difference between these two values, that will tell me the mass of the lead-2 iodide or my solid that's produced. Okay, so the mass of the PbI2 is 1.698 grams minus 1.462 grams, and that gives me a mass of 0.236 grams. So now that I know the mass, I can use my periodic table to figure out the molar mass of lead-2 iodide, and I can substitute them into the formula N equals M over M to find the moles. So the moles of PbI2 is 0.236 grams divided by its molar mass, which is 461.0 grams per mole. Grams cancels out, and the mole will reciprocal to the top, and that will give me 5.12 times 10 to the minus 4 moles of solid precipitate PbI2. Okay, so the actual calculation is not too difficult. It's just interpreting that lab data and understanding how that lab data helps us do our answer. Let's try another one more. This again is from one of the older AP Chem free responses. This one, the chemical equation was given to me in the question, so I just pre-wrote it there. And I'm being asked to calculate the moles of Na2CO3. So that's actually one of the original reactants. So the data table is not as detailed, but again, I'll try to sketch it out. It says here I have a volume of sodium carbonate. So let's pretend I've got a beaker and I've got 50 milliliters of sodium carbonate, Na2CO3. And then I guess just by reading the data table, it looks like what I'm doing is I'm adding a volume of 100 milliliters of calcium nitrate. So calcium nitrate is going to be added to the solution. And when it gets added, it'll be like 150 milliliters now. And not only do you get an aqueous product, so you get a sodium nitrate that's aqueous, but you also get a precipitate again that forms here, calcium carbonate. So I'll draw a little precipitate here. So this is my calcium carbonate precipitate. And it's given me a mass value as well. I think that's all we need to really draw for our lab kind of visual. It says here to determine how many moles of sodium carbonate are there in the original 50 milliliter solution. So it is a solution, and there is a mole formula, moles equals concentration times volume, but I don't have the concentration of sodium carbonate. That's not given to me. The volume is given to me, so I don't think I can use this formula to find the mole value. But what I do know is there's a lot of information about the product. If I go over to the product side, I know that the calcium carbonate, it has a mass of 0.93 grams. So what I can actually do is turn calcium carbonate into moles by using my mole formula. Remember, N equals M over M. And I can do a mole ratio. These occur in a 1-to-1 ratio. Again, the equation is given to me. It was pre-balanced. I could do a mole ratio to determine how much of the sodium carbonate I actually have. So let's first figure out how much calcium carbonate I have. It's going to be 0.93 grams over the molar mass, which is 100.1 grams per mole. So I have a mole value of 0.0093 mole of calcium carbonate. Okay, now let's go over to our reactant side to do our mole ratio. Now, again, it is 1-to-1, so the answer will be the same thing, but I'm going to show my work, okay? So what I do is I'm going to take the moles that I just calculated, which is 0.0093 mole of CaCO3. I'm going to set up a ratio where I put the units that I don't want on the denominator. So for example, in this case, I don't want the moles of calcium carbonate. So I want this to cancel out, moles of calcium carbonate to cancel out. And I do want the moles of sodium carbonate. So I'll put that on the numerator. And then in my ratio, what I can see is that for every 1 mole of sodium carbonate consumed, 1 mole of calcium carbonate is produced. And so the mole value of my sodium carbonate is also 0.0093. And yes, you should definitely show your work. It's always good to show all of your calculations to show how did you actually get the number, even though it ends up being the same number. Show your work so that we can see how did the units cancel out and how did that final answer get derived. Okay, so again, not a terribly difficult calculation, but hopefully we understand how to interpret lab data like this when it's given to me in a chart. And hopefully that helps a little bit. And you're welcome to leave any questions you have in the comments. Thank you for watching and have a great day.